don't know.
No.
Okay. All right, we're recording. Hello, welcome. I am Nicholas Canis, and today I'm going to be presenting to you about transformers and remote sensing, very high resolution imaging, and under that we're going to be focusing in scene classification for remote sensing. So remote sensing, scene classification, images under analysis, they are divided into patches, converted to sequence by flattening and embedding, keeping information about the position, embedding position is added to these patches. As you can see to this image to the right, A, B, and C are all the same images but over a different period of time, accounting for cloud coverage and land changes. And as you can see, the images all have color-coded regions, and the color represents, there's a color associated with each name of the crop. So for an example, white is rice, orange is, I think that's orange, I'm not really sure, I don't think it is, but each color is associated with the crop. And this is a good visual crop classification mapping. This is what this is a process of identifying and mapping the types of crops grown in a particular area, also known as CART, C-A-R-T, which is classification and regression tree. That's the acronym. This is a machine learning algorithm that can be used to create a crop classification map. Problem. The biggest problem is that there's such a big amount of data of these images for humans to sort through, take years, or just never get accomplished at all. The solution to that problem is using machine learning techniques to sort through these images fast and effectively compared to us humans. So effectively interpreting remote sensing images, uses for land management, urban planning, and modeling wildfires. Solutions are using transformers. They rely on a simple but powerful procedure called attention. They focus on certain parts of the input and get more efficient results. And they use deep learning methods to improve accuracy. We'll get into it later on into the presentation using the learning model that we used. We had to use scikit-learn, and scikit-learn is a library in Python that provides many unsupervised and supervised learning algorithms. Welcome to the class, Drew. Scikit-learn provides these for machine learning. Regression, including linear and logistic regression, classification, including k-nearest neighbors, clustering, including k-means and k-means plus, model selection and processing, which includes min-max normalization. So overall, scikit-learn is a powerful and flexible machine learning library that is widely used by researchers, practitioners, and educators. Its ease of use, consistency, and built-in tools make it, even for the most experienced users, an excellent choice to provide powerful and flexible tools. AgriField Net Competition Dataset. This is what we used in the learning model. Top line is the name of the data set. The images are readily available to the public, and notebooks from the competition are also readily available. And the rough estimate size of the data set is 309 megabytes, and when running the model, it is downloaded and extracted into Jupyter. This data set is a collection of satellite imagery and ground truth data related to agricultural land cover classification. Data set includes high resolution imagery, covering several regions, in this case, northern India. Contains 13 different classes in the data set, including farmland and 12 crop types. Pretty interesting fact, ground truth data was collected through field surveys and is provided in the form of polygon labels, which indicate the location and type of crops grown in each field. The materials and methods that were used, first off, we used the random forest classifier for scikit-learn. The random forest classifiers and meta estimator that fits several decision tree classifiers on various sub-samples of the data set and uses averaging to improve the predictive accuracy and control over fitting. The vision transformer, which is mostly done in my research, is an architecture that is based entirely on the vanilla floor, or the vanilla transformer, and there's an equation for that underneath. The vanilla transformer is a state-of-the-art performance in machine translation and other NLP tasks. A sequence-to-sequence modeling consists of an encoder and a decoder. It follows the encoder-decoder architecture with the ability to process sequential data in parallel without relying on any recurrent network. The linear embedding layer. Before feeding the sequence of patches into the encoder, it is linearly projected into a vector of the model dimension D using a learned embedding matrix E. The embedded representations are then concatenated together along with a learnable classification token V class that is required to perform the classification task. The resulting embedded sequence of patches with the token Z0 is given in this equation below. Here we have a process flow chart of what I just talked about. As you can see, the letter A, this image right here, it's sliced into 9 pieces. Just to demonstrate it's not necessarily going to just get sliced into 9 pieces, a lot more actually, laid out in a linear fashion for linear embedding, and then goes into the transformer encoder, and B and C just kind of show all the other background work of the transformer encoder. Then flows into the classifier and becomes class layer. Okay, using CUDA in PyTorch. So PyTorch itself is an open source machine learning framework based on the Python programming language in the Torch library. CUDA, which stands for Compute Unified Device Architecture, is a parallel computing platform and programming model developed by NVIDIA for general computing on graphical processing units, or GPUs, since GPUs have a significant or a higher amount of CPUs to use than just the actual CPU of compute. Some additional information about CUDA. It works with multiple CUDA devices, training a PyTorch model on a GPU, parallelizing the training process and running a PyTorch model on a GPU. CUDA helps manage tensors as it investigates which GPU is being used in the system and gets the same type of tensors. It also accelerates computations using the parallel process power of the NVIDIA GPU. Radiant ML Hub was something that we used for this learning model. It's an open library for Earth observations and machine learning. We used a custom API key, and for that we can download and extract data sets. Tutorials and notebooks are offered, which is what we used. Must be installed in the PyTorch environment, and the version 0.5.5 must be used in order for this notebook to actually work. Yeah, the AgriFieldNet India competition. This notebook loads data and builds a baseline model for random forests on the Niagara Field Net competition data set. To the right, we see libraries that need to be imported in order for the model to work. And right here, we're selecting the desired bands. And as you can see, there's quite a few bands. So for simplicity, only 4 out of 12 bands are selected for this baseline model. The data in this data set are originally adapted from 12 Sentinel-2 imagery bands. The selected bands will be band 2, band 4, the red, blue, green bands, and band 8, the near infrared band. Okay, so downloading the data set, as you can see, we got a little snippet of the code. The main, obviously, we're pulling it from the source, and we're also trying to set up and extract the assets, field IDs, and raster labels. And then we're going to put it into source, labels train, labels test. And now that we made those parameters, we're going to fetch the data and put them in their desired locations that we just made. So there's dictionary of the labels train, the labels test in the actual source itself, and then we'll download the actual data, download the data that we desire. Prepare the train data. First, we're going to load collection JSON and labels train collections paths and retrieve all unique folder IDs into a list. Then we're going to use unique folder IDs to create a list of field.tiff and raster labels.tiff paths for all tiles. Create a competition train data frame for all folder IDs and field paths. We're going to then create field crop pair data frame using field crop extractor. Then we're going to create train data frame using field extractor with args, competition train data, source collection. Group the process data set by fields and find the pixel average across the entire field. Merge train data frame and field crop pair data frame field ID. And then eventually we're going to split train df data frame for model training and evaluation. Okay, so creating IDs and folder paths. This top code right here, it loads a JSON file creating a collection of data and retrieves unique folder IDs from the file. It then creates a list of field and label paths for all tiles in the collection using folder IDs. The second snippet below creates a panda data frame called competition train data, and contains 2 columns, unique folder ID and field paths. And in the output below, it's just showing the first 5 rows of that data frame. Extracting field crop pairs. This extracts pairs of field IDs and crop IDs from the collection of the image data. The raster is used to read the field IDs.tiff and raster label.tiff files for each tile, then stored in field and crop data locations. Okay, so this input right here, the field crop pair, is a function that calls the extractor function with the list of train folders. The resulting pairs of field IDs and crop IDs are assigned to the pandas data frame, which is then displayed as the first 5 rows of that data frame. Now we're training the data. There's a function that's not shown because it was too big. That was called the feature extractor, which this function prepares the image data used in a pixel-based random forest model by creating an X variable where each row is a pixel and each column is one of the band observations mapped in its corresponding field. The snippet right here, the train data snippet, is calling the function feature extractor to extract the features of the image data, and the output is displaying the 5 rows of the data frame. Okay, so right here we're using scikit-learn metrics, and this snippet from scikit-learn metrics import. It's a function that requires the true labels and the predicted labels as inputs. In this case, ytest represents true labels and yprep represents the predicted labels. This then will print out, as you can see on the right, print out a report showing various metrics such as precision, recall, F1 score, support, and down below is accuracy, micro average, and weighted average for each class. Okay, we're extracting field crop IDs. The snippet above is a JSON file loads its content into labeled JSON. The last 3 lines we had to use because when extracting the information or the data, there would be a hyperlink at the end of the list, so we had to remove that. That was causing a lot of errors and a lot of frustration. The second snippet below is an empty dictionary called cropdict. This will be used to map numeric crop labels to corresponding crop names. And when we print out the actual dictionary cropdict, as you can see, there's a numeric value associated with crop. The input is a function labeler that takes an array of labeled fields as inputs and returns a corresponding array of crop labels using the cropdict dictionary, as I showed you before. The second line, right below the labeler function, this is generating predictions for the test set using the fitted random forest model. And this also generates the probability estimates for each class and the target variable, given the predictor variables. This probability estimates are stored in the predictions. The output, as you can see, the lower left-hand corner just displays the probability estimates for each crop. And in conclusion, we went over from that sensing classification, the problem and the solution. We went over AgriField Net competition data sets using CUDA and PyTorch. Also, it was used on the Ohio supercomputer and also on my own personal device. We went over training the data with random forest classifier and using scikit-learn, and went over the results. Any questions? Questions, Jerome? Okay, thank you very much for your time.
Very good.
Good, thank you.